Hello everyone, you are watching AWS and Machine Learning series, and this current topic in this lecture is data cleaning strategies for missing values, and especially we are going to touch now impute, compare and extensively analyze mean, median, mode and constant imputation strategies. This is lecture number 33 in this series given by myself, Shanaz Malik. Let's move on quickly. As I have been, I've shown you in the previous lectures, if you are with me, workflow to detect missing values. And once we detect, we need to convert all missing values to null values. Let's assume that we have done all that stuff and then analyze the amount and the type of missingness in the data. I have shown you all that stuff, and then appropriately delete or impute missing values. Well, I have shown you, deletion method, how to delete if you need, if you think that that's the right way. But here in this lecture I'm now going to show you imputation strategies, so how to impute missing values. And once we apply strategies, we need to evaluate this as well. And the more we are going to move forward in this lecture series, the more advanced methods you are going to learn. And just keep in touch with me. So let's impute missing values. Now, basic imputation techniques are constant, like imputing zero, mean, median, mode. Mode also means most frequent observation occurring in the feature. So we'll keep this lecture series concentrated towards these ones, and the more advanced one will be in coming lectures. So let's open our Jupyter notebook and learn about these techniques. Okay. Without any wasting further time, so here it is. So what I have done this time is that I have already executed all my code, so I won't be waiting for execution of any code, because if you see, the line 1 is already there, line 2 already showing me everything. So I'm not going to run anything, but if you are going to do it, you might need to first run. So what you need to do, once you open this notebook, all you need to go into cell, and if you highlight the top cell, and you can say run all, and then wait. And if all folders and all links are correct, then basically you will also reach this point, and then from there you can just see what just understand the explanation. So here it's simple. I'm not going to waste any time further, as I have done it number of times now. This cell simply sets the width of Jupyter notebook to 100%, and this simply brings the image which is inside photos. Okay, it brings it in here and just gives a fancy touch to presentation. And now data acquisition is happening here. If you see data acquisition, and I'm loading libraries NumPy and pandas for data analysis and data wrangling, and I'm using pandas function from pandas read underscore csv. And this time in previous one I have used a diabetes CSV, but this time I have just given you a different data set, or same of diabetes, but this belongs to Pima underscore Indians underscore diabetes X ls file. And what I'm doing, I'm taking this file and putting it into data frame df. And I'll show you why I have taken this data set and not the previous data set, because this has missing values which will help us to analyze and impute missing values, just to understand the topic in bit more depth. Now here I'm just doing, taking the sample of this data frame. Okay, here is the sample, and if you see, I have some missing values are there, and this is a sample. I've not taken the head and the tail, because that you guys know now how to do that. And then I have also taken, I have taken some info on this data frame, and basically, this is a concise summary of a data frame. And if you see that here, I have 768 entries, okay, from 0 to 767. And if you see here, I have all pregnant. It's a good healthy data set, looks like, at least to me. And if you see here, skin fold has only 541 healthy data observations, and rest are missing. And if you see serum insulin, has 394 out of 768, so it's a lot missing there, and nearly half of the data missing, and some missing values here, some missing values here, and the rest looks good. And BMI have few missing values. And rest, if you see diabetes, age, class, they are all healthy data sets, at least looks at the beginning. Now when you describe this data set, if you see BMI, a minimum is now 18, is not 0 as it was in the last case. So I have taken that case out, and just to concentrate on some other weaknesses of the data. So if you see, looks good to me at the moment. Okay, except there are some missing values, and let's analyze this missingness percentage. Okay, now what I'm going to do, I have data frame DF already, and I'm going to check, is null function on it, and save it. The nullity, and save the nullity of this function in df underscore nullity. Okay, and once because I have already executed this far, this line I've executed all. I'm not running, but you can run if you haven't done it until now. So, and then basically I'm checking the head of this new df nullity, and then if you see, this is just gives us the true and false, and where there's a true, that means it is a missing value, and where there's a false, that means it's not a missing value. So basically, if you add, and then you can find how much is missing and how much is healthy. And now here, if you see, I am summing up, as I said, it gives true and false. So if you sum up each column, what will happen? Here is df underscore nullity, and I'm summing up, and basically what it gives me, how much is missing. And if you see, skin fold has 227 missing, and serum underscore insulin has 374, and there are some other missing values as well. So now you can now see that your data is having kind of missingness. And now the percentage, if we have to check the percentage, all we do is we have this df underscore nullity, and which we see the mean of it, and times 100, and that gives us the percentage of our data frame. Okay, and if you see, and the percentage of the each feature here is given. Now if you see, we have 29.5 is nearly 30% missing here, and here nearly 49% is missing if serum underscore insulin. And rest few percentages also of diastolic underscore BP, and BMI is 1.43, and whereas diabetes is 0 and 0 and 0. Okay, so basically it gives you the percentage. And now you can see that, each feature, how much percentage is missing. Now let's visualize it, and to visualize missingness, I have said you in the previous lecture, and here I repeat, missing no is a wonderful library which can help us, one of the wonderful library, which could help us to visualize the missingness within our data frame. And I'm just as I'm going to use matplotlib with it, and just putting this magical function of percentage matplotlib in line, so that we could see our plots on the Jupyter notebook, and just to see available styles, and in the in our matplotlib pyplot, and here are some of them, and I have just chosen the one from here. If you see this Solarise underscore light 2, chosen this one for my plots. You can choose anyone basically, okay, depending upon what colors you like, and depending upon your eyesight. I'm just showing you all this because sometime for a person who's working for a long time, more than 7-8 hours, sometimes people work 17-18 hours a day, including weekends, and they have to kind of keep their screen as black as possible, so that the minimum strain to eyes is given. So let's come back to it, and here I'm plotting the missingness in the data frame. Okay, I'm using the bar from missing no. Okay, and I'm using the bar, giving some parameters, and here it is. It's this now visual presentation of the same thing. This is really to the point. Bars given, bar chart given for our missingness. And if you see that, for example, pregnant is healthy data set, all values are there, it's showing 100%, and here is a little bit less. Okay, 763, if you see, it's not touching the 100% mark. So, and 733, it is somewhere around, in 90s. And if you see 551, it is skin underscore fold, and if you see, it's showing the percentage, how much percentage is healthy and how much is unhealthy, and also tells you which column, which feature is more affected. And you can surely see serum underscore insulin is most affected feature in our data set, and then skin fold. And I can sort it, and you can clearly see it, but that's not a point at the moment. At the moment, the point is to just see the healthiness and the weakness of our data set. Now let's plot the nullity matrix of our data frame. And so all I have to do is give, instead of bar, I'm going to give matrix, and this will plot nullity matrix of our data frame. And the parameters are as here. And here it is, this is nullity matrix. And if you see these white horizontal bars, shows us the missingness. So if you see, this is our first observation, and it goes to the down. And if you see all observations healthy, and some observation here, in glucose is there is few missing values in glucose. And if you see, this is, it shows us where actually the missingness is. Okay, is it at the beginning or at the center or all the way? For example, if you see serum insulin, it starts from start, and every now and then it's missing. And same is case in skin fold. And it kind of shows, kind of tells us that if this is missing, and if this is missing, most probably serum is also missing, or something like that. And BMI, but I'm not yet putting that statement, but just giving you, showing you how visually it could appear when we use missing no dot matrix. Okay, and if you see, there is some random BMI also missing. Rest are healthy data sets, and that's excellent news for us. We have 9 features, and 1 column affected, 2 column affected, 3 columns affected, 4 columns affected, 5 columns affected, right? So 5 columns you have missingness, and 5 columns you have missingness. That's okay. Now sort. Now if we sort diabetes data frame, which is in our case it is DF, on serum insulin. For example, if I'm going to sort on this now, and let's see what it produces. Okay, so what I'm doing, I'm taking my data frame, I'm giving the sort function to it, sort underscore values, and I'm saying give me sorting by serum insulin. And then basically once I do that, I store the sorted values, and then instead of giving df here, I'm giving now sorted data frame with respect to serum underscore insulin. And what I can see, that where this is missing, and the same thing is happening, this is missing and this is missing, and and mostly where serum is missing and skin fold is also missing. So it's giving you kind of so if this is you have this observation, and same you have that observation as well, but if this is missing, most oftenly skin fold is also missing, and there are some observations where diastolic underscore BP is missing as well. So let's move on. So the correlation between missing data, missingness. Okay, remember we could find correlation between missing data, and it helps us to gain a deeper understanding of the type of missing data. It also provides suitable ways in which the missing values can be addressed. Now there's another way, a heat map, of the same data frame. That we have connected to DF is a diabetes data frame, Puma, diabetes data frame. But what I mean to say, that if you give this data frame to heat map from missing no, what will happen then? It gives us the correlation between various features. Okay. Plots the correlation of missingness between various features. And if you see here, if you see anything in pinkish, towards pinkish, that is strong correlate positive correlation, and if you see something towards reddish, that is strong negative correlation, and if you see something in the greenish, that is near to zero correlation. So for example, there is this stuff, anything glucose with BMI has nearly zero correlation, and glucose with serum underscore insulin is zero point 0.1, and this is minus 0.1. So, but what we could see from here, very important case is if you see skin underscore fold, okay, skin underscore fold with serum underscore insulin has positive correlation of 0.7, and that is something to note, and rest are 0.3 and 0.3 here, okay. Diastolic underscore BP with BMI is 0.3, and the same is with the skin underscore fold. So but the most strongest correlation is between positive correlation between is skin underscore fold and serum underscore insulin, that is 0.7. It's somewhere in this area. So now let's plot dendrogram of our data frame that we have connected to. So it's simply missing no, we give it to missing no, and then pass the dendrogram function, through we use dendrogram function for this data frame that we have connected to, and and give some parameters, and here is our dendrogram. Okay, now if you see that dendrogram makes a cluster, closely, where it finds a correlation, and it kind of creates a cluster. And if you see the skin fold, skin underscore fold or skin fold, and serum insulin has a strong correlation, okay, and they're kept in separate group, whereas class, age, pregnant, and diabetes is in one group, and glucose is kind of close towards the class and age. But if you see glucose is bit close to BMI, and then diastolic underscore BB. But here again you can see that correlation that we have found in here. If you see skin fold to serum insulin has 0.7, the strongest correlation, and same thing you could find through dendrogram as well. Okay, so these are, you are visualizing everything now. More on the topic, we could write some useful functions. If you see that I'm importing rand from numpy.ran, and I'm writing a function that automates creating dummy values for missing data. And here is I'm giving it fill underscore dummy underscore values, and the parameters which it will take is data frame and scaling factor, and I have given a if you don't provide a scaling factor, that's going to be 0.075, but you could play with it depending upon your case. But I have taken it after I've checked, and for me it suits, and for you, you could check and see which one suits for yourself. Okay, what I'm going first of all doing, I'm doing a deep copy of my data frame, and then using copying it, and saving it as df underscore demi, and remember that we are copying it as the parameter deep is equal to true. And now then I'm giving a for loop to this demi data frame, and going through columns, and then if you see that I'm getting the column names and storing them in here. It's basically then simple. If you see column is null, putting them here, calculating the number of missing values in the column as we have been doing still until now, and then calculate column range, which is column maximum minus column minimum, and storing it in column range. Then shift demi values to -2 and -1. Remember, rand generates values between 0 and 1. That you should, all guys should know. This function generates values between 0 and 1, but I'm just shifting values, and I'm just shifting values if you see by just adding -2 to it, and Okay, and basically, what it does, it will create values between -2 and -1. And then I'm scaling dummy variables by scaling factor. Scaling factor is given here, and then times column range and plus column min. This kind of scales dummy variables by scaling factor and shifts them towards column min. That is BMI underscore mim. I don't think it should not be. Okay, so and that is column min, and then basically what it does is then I'm returning dummy values. Okay, and this is what function basically does. Returns you dummy data frame. Okay. So this function automates and creates dummy variables for your missing data in your data frame, and then generate a scatter plot with missingness. Okay, now what I'm going to do is fill dummy values in the diabetes underscore dummy. So if you see here, so here is our now this function. I'm giving it to my data frame, and then it gives and storing those values here. Okay, and diabetes underscore dummy, then sum the nullity of serum insulin and this for coloring. If you see, just taking this column and checking the nullity and the same nullity, and same here, checking the nullity here, and then storing that sum inside this variable. And here I am creating a scatter plot of serum insulin and BMI. Okay, and that's simply I am and now taking this data frame and plotting and giving X serum insulin and Y BMI, and rest of the parameters, if you see, it all makes sense. If and once you plot that, and if you see now, here is serum insulin on the x-axis and BMI on the y-axis, and if you see what has happened, if you these are your variables, and if you see these are where the data is missing, and this is where the data is not missing. If you see, the reddish is 0 and the pinkish is 1, so the pinkish ones are showing that where the data is missing. Okay, so these are the data points where the serum is missing with respect to BMI. If you see it's scattered all over, there's not much correlation visible in it. So excellent. So now from above plot, let's make sure that we take close look at how the missing values of serum insulin and BMI interact with each other. We don't see any specific correlation between these two variables that is of missingness of this and that. Okay, I mean to say skin insulin and BMI, because it's straight, as if you see, this is a bit scattered, this has a kind of a positive relationship, but here it goes all the way up, so it stays kind of moves towards the y-axis, whereby x-axis is kind of ignored. So there's not much correlation seen. There's not no correlation seen there. So let's find the interaction between serum insulin and BMI. Same thing. I'm not doing any fancy stuff, but all I am just changing the features. And if you see now, here again the same stuff. Okay. So it's a type of missingness, and you could see, check the correlation of various variables with respect to each other. Now remember, we have already discussed and performed deletion tasks. Just to recall, deletions of our two types: pairwise deletion and listwise deletion. Listwise deletion is also called as complete case analysis, and used when the values are MCAR, list-wise and pair-wise deletions are most commonly techniques to handle missing data. It's important to understand that in the vast majority of cases, an important assumption to using either of these techniques is that our data is missing completely at random. Okay. That's what I was saying. In other words, the analysts or researchers needs to support that the probability of missing data on their dependent variable is unrelated to other independent variable as well as the dependent variable itself. So just keep this in mind. We have already gone for the deletion stuff, given some examples, some tasks in the previous lectures. Here we are going to see what's now what strategies are, if we use mean imputation strategy or median or mod or imputing a constant. So basically what I'm doing, I'm copying again a data frame, using deep is equal to true and creating a data frame, and then from sklearn, I'm impute, and sklearn impute, I'm importing simple imputer. Okay, and then this using this instance of simple imputer, and through the strategy, I'm using a variable mean in giving a parameter mean to strategy. Okay, and then basically I'm creating this instance mean underscore imputer, and then on this mean underscore imputer I'm activating fit underscore transform function and giving my this diabetes underscore mean data frame, and then basically here I am going through all columns and all rows, so all features and all observations, and basically performing fit transform. Okay, and that's it basically, and this is the way you do the imputation. Okay, mean, and same thing happens for median imputation. Or this is all same, all you have to give the strategy is equal to median, and rest remains the same. And same is for mod, most frequent in the strategy, and rest remains the same. And if you see now a constant, if you are just imputing a constant, and then the strategy remains as constant, and the additional parameter you have to give fill underscore value is equal to 0. So here I am imputing 0. Okay, here I'm imputing 0 in our missing values. So basically rest remains the same. And let's plot a scatter plot of imputation, and here what I'm going to do, I am going to impute. If you see, I'm just checking the nullity, and then basically if you see diabetes underscore mean, I'm taking this data frame, which means the first whereby I have imputed mean. Okay, so if you see this mean, okay, so here, so I'm taking this data frame where the mean is imputed, and I am just and then I'm plotting on x-axis serum insulin and on y-axis BMI. And if you see that imputed ones, the values which are imputed remains kind of goes towards the x-axis, but they are not moving on the they're not moving on the x-axis, but they're only moving on the y-axis, but whereas you see the original data, which is a non-missing data, has kind of a correlation, kind of a positive correlation, but this is not catching that stuff. So we are imputing, but we are creating this. What I mean to say by imputing, if we implement this strategy, mean strategy, what we are doing, we are basically adding a bias in this data set. Okay, because if you see, we are adding our we are converting our NAs into some data, not some data, into mean in a data, but the correlation is lost, and which means that we are basically adding a bias to this data set. And if we implement this strategy, this bias will be transformed into our machine learning, and hence our model might not give as best results as would be possible if we use some advanced or some other imputation strategies to impute these missing values. Now, comparison of the different imputation strategies and their visual analysis. Now, if I have to do, I need to check it for each, for median, for mode, for constant, and whatever I'm using. But to do that, I'm not going to do it now by one. What I'm going to do, I know that I have 4 strategies to check, so I'm just going to create 2 rows and 2 columns, and have my 4 figures in that. And then I'm going to do the same thing, but basically I am creating a dictionary whereby I have these imputed data sets. Okay, data sets where I have imputed values of missing value. Okay, so this one we checked, but I'm checking this again, and now it's median, mode, and constant, which I created above, and putting this in the dictionary. This will be dictionary key, and these are values. And then basically I'm going to use this dictionary. If you see, then I'm creating a for loop, and basically accessing my imputations, which is my dictionary, through the dictionary key, and plotting, okay, all that what I need to plot. And then if you see, here is that wonderful stuff. Mean imputation is here again. It's not catching the correlation between serum insulin and BMI. Same happening with the median, not catching the correlation. If you see again, the data is here, seems to be a bit, it shows me some kind of scatteredness is there, and some kind of positive correlation might be there, but or imputation method median is not catching that stuff. And same is happening with the most frequent imputation and constant imputation. Okay, so what does this tell us? The summary is the clear correlation between non-missing plotted features that are missed in overall imputation strategies, and this creates a bias, as I have said, because it's not catching the correlation. Okay, so if it's not catching the correlation, then if we use one of them, one of these strategies, then we are creating a bias. Okay, and imputation strategies do preserve their basic statistical properties, but don't account for their correlation. To deal with this, and this is a real world problem, we need a more robust imputation strategies, and that we will learn in next lecture, or coming lectures, I could say. With this, if you like this video, if you like all what I have shown you until now, then just please comment how you like this video. Please do comment, and I also request you to please subscribe if you haven't until now, and please hit the notification bell so that you get notified as soon as I upload new videos. And I hope to see all of you in next video. Until then, I thank you all for watching. Data analytics professionals, remember, sharing this video is caring for yourself, caring for knowledge, and caring for the society. And I strongly suggest to share my videos with your colleagues, peers, juniors, seniors, and maybe somebody might share it with somebody else who might be in more need than you and me. I thank you all, and it's time to say goodbye.